In this lecture, we will see the schematic diagram of a 2-input XOR gate using 2 transmission gate, and then how to draw the layout from this schematic and the twisted schematic. This is a 2-input XOR gate using the transmission gate. Now let's see what is the symbol of a XOR gate. The symbol and the corresponding function. The symbol of a XOR gate is this is A, this is B, and this is Y. So we write Y is equal to A XOR B. Now if you expand the function, the function of a XOR gate is written as Y is equal to A bar B plus A B bar. Now let's see the truth table of a 2-input XOR gate. We'll see the truth table of a 2-input XOR gate. It has got 2 inputs, so make a table. This is A, this is B, this is Y. 0 0, the output is 0. 0 1 1, 1 0 1, 1 1 0. So if you write one line for explaining this truth table, then it will be when both the inputs are same, then the output is 0. Otherwise, the output is 1. That is, when A is equal to B, then Y is equal to 0. If A is not equal to B, then Y is equal to 1. Now in order to find the schematic, or in order to draw the schematic diagram, you have to follow two processes. Schematic diagram is very essential in order to prove the truth table. So now let's see the schematic. the schematic diagram of 2-input XOR gate. Okay. Now if we go by the function of a XOR gate, that is y is equal to a bar b plus ab bar, a bar b plus a b bar. So here we need two inverters, two AND gate and one OR gate. 2 AND for getting a bar b and ab bar, and 1 OR for this whole function. So if I draw a schematic, then it will be two inverters. So this is one inverter, this is input A and the output is A bar. Then you have another inverter, this has input B and the output is B bar. This is VDD, this is the ground, this is the inverter, only opting the A bar and B bar. Then you need to AND. So there will be two circuits for AND. Then again for AND circuit you need the two NMOS in series and the PMOS in parallel. This is A, this is the second input B. If this is, let's say this is B bar, then the second input will be A and this is ground. This is B bar A, then there is A bar B. So again you will need a schematic over here, and finally will be the OR gate. So if you want to draw a bigger schematic, then we need to draw it on a bigger page. Before that, let me clear this. The function is a bar b plus a b bar. A bar b, then there will be two inverters. One for, if this is A, then this is A bar. If this is A, then this will be A bar. Then similarly we have B and B bar. This is B, this is B bar. So you need two AND gates. One is for A bar B, so this is A bar B, and next is A B bar. Then now in order to construct two inverters we need two PMOS, two NMOS. Then for two AND gate we need four PMOS and four NMOS. Then for one OR gate we need two PMOS and two NMOS. If you make a total of it, then the total PMOS needed is 8 and the total NMOS needed is also 8. Okay, total PMOS and NMOS needed will be 8 and 8. So we have to find a way in order to reduce this number of PMOS and number of NMOS. Okay. So if you see normally through the normal schematic by using 8 PMOS and 8 NMOS, the first is the normal schematic using 8 PMOS and 8 NMOS. Okay, using 8 PMOS and 8 NMOS. So first is inverter. So as we know, this is PMOS 1, this is NMOS 1. Input A, output A bar. Then we need the second one to speed it. This is input B, output B bar. Then we need two AND circuits where the NMOS is in series and the PMOS is in parallel. Two such AND circuit. and a, this is we need a OR circuit where the PMOS is in series and the NMOS is in parallel, where all these are connected to VDD and all these are connected to ground, and this is VDD. So now you can see that the schematic is too difficult and the layout will be more difficult as it appears from the schematic. You can just give the inputs. This is A bar B, this is for A bar B, this is for A B bar, and this is the final output A bar B plus A B bar. You can make the connections over here. Okay. So what can we do in order to reduce this number of gates, or the number of PMOS and the number of NMOS? What can be done? We'll use transmission gate, because we know the transmission gate is very useful in designing the XOR and XNOR gate. So let's see how this is easier to use a transmission gate in order to design these XOR and XNOR gates. So now, okay, before that you have to make sure this A bar means you'll take from here. This in output, what the inverter 1 will act as input of the AND 1, and the input of inverter 2 will act as the second input of AND 1. Similarly, this is the first input of the input of first inverter, and the output of the second inverter will act as the input of the second and the output of AND first and second AND will act as the input of the OR gate. Okay. Now we will see the schematic using the transmission gate. Let's see the schematic diagram of a 2-input XOR gate using the transmission gate. Schematic diagram using transmission gate. Okay. So the schematic diagram will be something like this. We'll use 2 transmission gate. So this is transmission gate 1. Then we'll have another transmission gate. This is the transmission gate 2. So you have input A. This is A input. The input of the second transmission gate will be the inverter of the first transmission gate, that is A bar. Then the control signals, as we know, they are complementary. So if this is B, then this side will be B bar for the first transmission gate. For the second transmission gate, if this is B bar, then this will be B. Now this is the output of the first transmission gate. This is the output of the second transmission gate. Then you have to connect these two. And the final output is obtained from here. Out is Y. Now how will you see that this is the correct output? Actually, how do you get this design, or how will you get the schematic diagram? You have to verify this schematic diagram with your truth table, the truth table of the XOR gate. So now let's see this explanation of this schematic diagram before going to the twisted schematic diagram. So we'll see the explanation from the schematic diagram. You can write explanation of truth table from schematic. Okay, so the first condition is if A is equal to 0 and B is equal to 0. Now when A is equal to 0 and B is equal to 0, then from our schematic diagram, this is the final output Y. This is the input A, this is the input A bar, this is B, this is B bar, and this is B. Okay, now let me label the input and output first. This is P1, P2, this is N1, this is N2 for this case. These are the sources, drains, sources, drains. Okay, now when A is 0, then certainly the PMOS will turn on and NMOS will turn off for both the cases. So here P1 and when A is 0 and B, right? So A is the input actually over here, A is the input while B is our control signal. So this will decide whether the PMOS will turn on or will turn off, similar with the NMOS. So here when B is 0, then this P1 will turn on. So P1 will turn on. Here B bar is given to N1, that is N1 will become 1. If N1 is 1, B is 0, B bar is 1, B is 0. Here A is 0, here A bar is 1. So now B1 is 1, B bar is 1. So here N1 will turn on. Okay. Here B bar is 1, that is 1 is applied to PMOS. So P2 will turn off. Similarly here B is 0. So when 0 is applied at NMOS, then that will also turn off. So the transmission gate 1 is activated. It's active and it is off. That is, input will not pass to the output. So here the input A will pass to the output. Input A equals to 0 passes to output. So Y is equal to 0. Actually Y is same as A. So here since A is 0, then output is 0. So if A is equal to 0, B is equal to 0, then the output Y obtained will be 0. So the first is satisfied now. Now let's see the second condition, that is if A is equal to 0 and if B is equal to 1. If A is equal to 0 and B is equal to 1, so we'll make the transmission gate again. Okay, this is A, this is A bar, this is B, this is B bar, this is Y. Okay, this is again B. This is P1, P2, N1, N2. So now here A is 0, A bar is 1. Okay. Here A is 0, A bar is 1, and B has the value 1, B bar is 0. This is again equal to 1. So now when this is the control signal, right? We know that this is the control signal and this A is only the input. So when B is equal to 1, then this PMOS will turn off. If B is equal to 1, then P1 will turn off. So here 0 is applied at NMOS 1, so that will also turn off. Now 0 is applied at PMOS 2, So P2 will turn on and B is 1, that is N2. At N2, 1 is applied. So this will activate N2. This will also turn on. So now what happened? This will totally, transmission gate 1 is off or cannot conduct, and transmission gate 2 is active now. Okay, so when transmission gate is activate, so Y will be same as the input, that is A bar, that is equal to 1. Whatever the value of will be at the input will obtain the same at the output. So here A bar is obtained at the output. So if A is equal to 0, B is equal to 0, then this is 1. If A is equal to 0, B is equal to 1, then the output obtained will be 1. So this is also verified. It is correct. Now let's see the third condition. The third condition, if A is equal to 1 and B is equal to 0, then what will happen? First, draw the schematic diagram again. Okay, this is P1, N1, P2, this is N2. So as we know that A is nothing but the input and B is the control signal. So here A is 1, so A bar will be 0. Here B is 0, then B bar will be equal to 1, B is equal to 0. So now if B is equal to 0, then 0 at P1, so P1 will turn on. N1, at N1 you get 1, so N1 will also turn on. Okay, as we know that at 0 the PMOS turns on and NMOS turns off. At 1 the PMOS turns off and the NMOS turns on. Okay, here 1 is applied at P2, so P2 will turn off and N2 will turn on. N2 will also turn off because here it is 0 applied at N2, so that will also turn off. So P1 N1 will turn on, that means transmission gate 1 is active. This is transmission gate 1, this is transmission gate 2. So this is active. So now and the transmission gate 2 is off. So now what will happen? Whatever will be the input A will be obtained at the output Y. So at Y, the input A is passed to the output Y. So Y will get A, that is equal to here 1. So if A is equal to 1, B is equal to 0, then Y is equal to 1. That is what we have obtained at truth table. So this is also verified. Now let's see the fourth condition. The fourth condition is if A is equal to 1, B is equal to 1. This is A, this is A bar, this is B, B bar, this is also B. Okay, so this is P1, N1, P2, N2. So when A is 1 and B is 1, both are 1, A is 1, A bar will be 0, B is 1, B bar 0, B is 1. So if B is 1, then P1 will be deactivated, P1 off, N1 0, then N1 will be also off. B bar 0, then P2 will turn on and N2 will also turn on. So here what will happen? Transmission gate 2 will be activated and this will be active, and this output A bar will be obtained at Y. So Y will get A bar, that is equal to 0. So if A is equal to 1, B is equal to 1, output Y is equal to 0. This is also verified. So the truth table that is verified from the schematic. So now we will see the twisted schematic diagram. Before that, the normal schematic diagram. You can see the normal schematic. You can see this is B and this is B bar, this is A, this is A bar. Okay, this is B bar. This is again B. And this is the output. That is Y. You can see there are two inverters here. So what you will do? Here you will need two inverters with input A, output A bar, another inverter, input is B, output is B bar, connected to VDD. These two are connected to ground. This A will be connected from here. Okay. A from here, A bar to here. Okay. This A will be connected to here. Okay. Now this A bar will be connected here. Then B bar can be directly connected to here, and B here. Then from here. Okay. So this is the normal schematic diagram. Now let's see the twisted schematic diagram. Now let's see the twisted schematic diagram of a 2-input XOR gate. So we have 4 PMOS and 4 NMOS. So you can see in the first discussed schematic there were 8 PMOS and 8 NMOS, but here there are 4 PMOS and 4 NMOS. This is 1, 2, 3, this is 4. These are 4 PMOS, then we have 4 NMOS. This is NMOS 1. Then similarly we have NMOS 2, NMOS 3. This is the NMOS 4. So now we have to connect this is the inverter part. So first design the inverter. This is the inverter part. So gates are shorted. This is input A. This is input A, and through the drain you get the output A bar. Similarly, this is B, and this is B bar. Okay. So now we actually know this is source, drain, source, drain, source, drain, source, drain. These are two inverters. They are again source, drain, source, drain, source, drain, source, drain. So I'm not labeling the sources and the drains because all are in the same pattern. So the VDD are connected. VDD. These two will be connected to ground. So the inverter is already designed. So transmission gate, the sources and drains are connected. Source to source, drain to drain. Then again source to source, drain to drain. This is input A, which will be connected to this. Okay. Now, before that, the gates are not joined. We know that the gates are not connected from the gates are connected in opposite manner. Okay, so this is A and this is A bar. So A bar means this A bar will be connected over here. So make a connection from this side. This is A bar, then you can directly connect from here. This is A bar. Now the output is this drain, these two drains. So these two drains are again shorted in order to get the output out. You can see the schematic is looking a bit clumsy, but you can draw the layout from this schematic. Now let's see the layout from the twisted schematic. It's a bit clumsy, so clear this. First draw the anvil. You can actually understand the whole layout once you see the layout in the next lecture. So this is anvil. This is anvil. This is the anvil. Then we have the P diffusion. Now to draw the PMOS. This is P diffusion 1. This is the P diffusion 2. This is the P diffusion 3 and the P diffusion 4. This is the P diffusion layer, and the P diffusion layer was brown in color. So if you want, you can just coat in brown. After drawing the P diffusion layer, we have to draw the N diffusion layer. So N diffusion layer is green in color. So draw the N diffusion layer. So there will be again 4 N diffusion layers. This is the N diffusion layer. After drawing the N diffusion layer, next draw the inverters first. So you have to draw the poly layer. So this is poly 1. This is poly 2. Okay, so this is poly. Now this poly is the poly or the gate of the two transmission gates are interconnected. So connect from here to here. Then similarly the opposite way. Okay, the gates are interconnected now. Now first complete the layout of this one inverter. So we know that the sources are connected to VDD. So this is the VDD layer. Then the sources of NMOS are connected to ground. So this is ground. Then these two drains are shorted. Okay. So if this is A, then this is A bar. If this is B, then this is B bar. Okay. So now we have to short the sources of PMOS and NMOS in a transmission gate and the drains of PMOS and NMOS in a transmission gate. Similarly, over here, this. So we know this is A, which is the output for Y, and this is A bar. This is B bar and this is B. So now in order to connect this A to A, this A, so we can connect from here. Because you have to keep in mind we could have done it directly, but here since the other metal layers are there, they will overlap. So this metal layers shouldn't overlap. So bring it to here. This is A. Then there is a overlapping between these two, and so we'll need a poly contact. So this is a poly contact. After connecting A, you have to connect this A bar with A bar, which can be connected directly from here. A bar is connected to A bar. So from here okay, so this is our A bar. Similarly, you have to connect the B to B and B bar to B bar. This B is, this can be dragged from here. This is B and this is B bar. So from here it is connected to here. Again we'll need a metal over here and a contact. I have to place a poly contact. Then the drain terminal is left out, where the two drain terminals are shorted. Here is the output Y. This is the output Y. Then you have to place the contacts. This is the PDC contact. And you have to place all the diffusion contacts first and then the substrate contacts. So similarly you have to place the contacts over here. So this is the PDC contact. As you have seen, this is PDC contact. Similarly, contacts over here. These are the N diffusion contact. These are the N diffusion contact. And after placing the diffusion contacts, next you have to place the substrate contacts, and the substrate contacts are placed in VDD and ground. So you can place one over here, similarly one over here. Okay. Now after this, after placing the contacts, you can just verify once more whether all the connections are done. Inputs given, output is labeled, VDD ground. Okay, so these are the two inverters. These two are the inverter 1, inverter 2, transmission gate 1, transmission gate 2. Similarly, you can draw the layout from the normal schematic diagram also, as discussed earlier. For the normal schematic diagram, the layout from the normal schematic, you can see here the transmission gate will be drawn exactly like this, and the inverter will be drawn exactly like this. As this is, suppose, the PMOS, then you have to take a anvil, then the P diffusion layer inside it in a straight manner like this format. But over here you will take the anvil as this and the P diffusion inside it. Okay, so you can understand, if this is in this format, then this will be the layout, and if this is in this format, then this will be the layout. So you can take the layout from the twisted schematic, which is a bit easier. You can just see the difference, which one is more easy, to draw from the normal schematic or to draw from the twisted schematic. Then to draw from the direct from the functions, or to use the transmission gate. If you use the transmission gate, you can see the number of PMOS and NMOS is reduced to half. If you use the normal function, then you will use 8 PMOS and 8 NMOS. If you use the transmission gate, you can see you need just 4 PMOS and 4 NMOS. So it's better to use the transmission gate in order to design XOR and XNOR gate.